Okay, so this is the third time I'm recording this lecture because last time my memory was filled, so I have to record this again. And before that, I get along with a call, so I have to do this again as well. So let's go. And let me remove this part so I can do this again. Okay, so for quantum physicists or simple physicists, quantum phenomena are really fascinating because they had to deal with particles at quantum level. They can build devices using those particles and their interaction, and can get along many useful applications. And it's really important for them to even use it because the new world and new era, new devices will be much more faster and much more applicable when you do them with a quantum perspective. So it's really fascinating for physicists to think about it. But what's in the deal for computer scientists? So computer scientists are not very familiar with quantum phenomena because it's not their field or domain. But it is now till we got the quantum computing field. So what actually computer scientists has to go through is like they have to build some certain algorithms and certain applications and certain rules and certain conditions to go through some problem, and they can solve it. But they have certain challenges, and one of them is the complexity of that algorithm that can be applicable on their hardware devices. So this is one of the most biggest problems they face around, and they came along with a new and better algorithm again and again by trying again and again, and came along with the solution of that problem. So this is very important for them, and what they can actually do is they can use the quantum phenomena in their application. And how they actually do this is something which we will be covering in this course. So complexity is a really amazing field in computer science, and it's actually one of the most important field in computer science, important domain you can say, because it actually leads you to the solution of problem with an easier way and using much less resources than an actual one. So this graph will actually represent two of the complexity problems which are actually important for this lecture. So x-axis shows you the input size, like how many input you can fit into the problem. Like it can be 1, 10, 20, 30, 10 million, 1 billion, whatever the size of n is. It can actually increase gradually or increase in exponential form, whatever. And here we have the time. Like if we have 100 number of input, what will be the time it will require to solve the problem? So we divide our problems into subclasses. So two of them are, which I'm going to define is, one of them is the polynomial time, n squared, and one of them is the exponential time. So when the problem is around polynomial time n squared, computer scientists are very happy. They're like, okay, so we can solve this problem with our algorithms, and it actually suits pretty well in our device or our hardware capabilities. So they're actually very happy with it. But when the problems are something which we call polynomial time, exponential time, it gets really difficult, because as soon as the input size increases, it's really difficult to manage it in our hardware resources, and it gets difficult to have the time control in our hands or in our situation. So this is something which is a big problem for computer scientists. So what we can do here, like this is a problem, what's the solution? So what we can do is we can convert our problems from this to this only by one thing, by creativity. That's it. You can actually convert this from this by only thinking, right? You can actually think along and came up with a new solution, and then it's good to go. And computer scientists like spent decades, 10 years, 20 years, and someone came along with a new sort of algorithm, even 100 years, even 500 or 600 years. I've even heard about the stories from our professors. So it's like really fascinating because you have to deal with this and convert this into this. We don't have much time, we don't have much resources to solve the problem. And it's really beautiful when you do the complex problem in the easy way. Like if I can move from this position to this position, right? So it's really easy, I can move along with linear path. But if I go this and move around like this and then move this, at this position. It's very bizarre and difficult, and even though I can do this, but it is something which is not preferred, and this is really not preferred, because if you have small amount of input, like if the input here is 10, you can actually do this in, if the problem is like exponential, you can do this like this. But if the problem is like suppose 100 million input size, it will get difficult to solve the problem in exponential form. You have to either convert it into the polynomial form, or you have to think something else, like another way which can be used to solve the problem in a very good way. So there is something else which computer scientists came with, is randomization. What we do here is like we apply a randomized approach, and then using that randomized approach, we solve our problem. Sometimes it performs well, sometimes it doesn't. So most of the time it performs well, and it lies somewhere about here. So it's like a minute difference in our complexity problem. Oh, I think I did it wrong. Yes, I did wrong. No, it actually converts it into polynomial, but the number of size of problems are increased. So I have to draw another diagram for it. I will actually mixing two of them in the same one. So this is suppose it's a big class, and it says that every problem is exponential, and it takes a lot of time and very difficult. And from all of these problems, there are few problems that can be solved in polynomial time. Let me check if my phone is still recording. Okay, it is, because last two times it was really difficult, because I was thinking that it's recording, but it wasn't. And this is exponential time, and this is someone came along and said no, this thing can be solved in polynomial time, and like this problem can be solved in polynomial time. So this is another subclass of this bigger class. And then someone else came along and he said that no, there is something else we can do, is bounded error probabilistic approach. So what we do here is like we apply randomization, and with the help of probability we actually use one of the options which we find suitable and solve using this probabilistic approach, and it's very good, and it outperforms the this subclass, and this can become another subclass which is a little bit bigger. There are some problems with this one. It's like there is a debate among computer scientists which says that this class is actually this class, and they are actually equal, like this, equal, and equal, and they are to some extent they are equivalent. We say this as equivalent. They are to some extent equivalent. So this is really fascinating, because it's a good approach if we actually solve some problems which are which were exponential before, but you apply the randomization approach and they came along with the polynomial time. It's very fascinating. And then come the main part, why we are discussing all of this, is quantum approach. So there is something else which we call bounded error quantum polynomial time. So what it does is that it actually uses interference pattern to go along in different possibilities and get you an answer. They actually have same approach, but here we are only doing it in deterministic approach, but with probabilistic approach. But here the probabilistic approach is actually having an interference pattern. It's like they might have same hardware, but this has to be solved with different hardware. And for different hardware, we will have different kind of softwares, and for different kind of applications. And this is really fascinating, because it actually applies the real world quantum phenomena into your computing device. So you need a different kind of hardware device which can actually implement the algorithms which are quantum algorithms and can be implemented inside our environment. Let me see if it's still recording, because it will be difficult to do this again. Okay, so this is the bounded approach, a bounded probabilistic approach, and this is the quantum approach. And this is where the fun begins. When computer scientists came along and said, oh, this is like really amazing that it actually disapproved the part that random approach is the best one. So quantum is actually performing well in this field, even though we have not figured out every algorithm yet which can be done with this one, because we don't have such hardware which can implement such kind of algorithms which we need right now and haven't been figured out yet. So there are some problems here which can be solved in quantum approach and not in an exponential approach, which is like really fascinating for computer scientists because it's really fast. They solve the problem in good amount of time. And one of them is like factorization. Like if you have factorization of a huge amount of numbers, so it's difficult to do this with the random, the different algorithms which are like deterministic one or probabilistic one, and then we came along with the quantum part. It can actually improve this. We have few algorithms which are Schwartz algorithm, which we will discuss in the next parts, like not right now, even like in the end parts. Next we will discuss about qubits and velocity and gates, which are like the amazing and heart of quantum computing. Very fascinating and amazing parts. This one is mainly defining the reason why are we doing quantum computing, quantum information and technology, and quantum information and computing science. So it's like you have one approach, you go from there, deterministic approach. You have multiple options, you choose this one. You have multiple options, you choose this one. You have multiple, you choose this one based on the random approach. And then you have the quantum approach. You have multiple options to figure out the multiple option. One option to figure out the multiple option, and then from the multiple option you came along with the one answer. This is the same as the probabilistic, but here it can be this, it can be this, it can be this. And in probabilistic it will be this for always, but in quantum it can be this as well based on the interference and based on the phase difference between both all of them, or whatever the amount of number we have to solve. So I think this was the end of the lecture 1, and it's really fascinating to say that lecture 1 was a lot about the introduction and basics. Not basics, but introduction sort of thing. You get to know about why are we doing this, we get to know about the phase, and you get to know about different representation, the matrix representation, which are like the start of it, but they can play a good part when you came along with this one, and you get to know more about it and into the practice part, so you can easily understand what you are doing. So this lecture was really important. It actually, I think, comprised of 8 parts or 7 parts. Each one, a few of them are 16-14 minutes long, few of them are 7 minutes long, 8 minutes long, 10 minutes long. So it's actually divided into this kind of intuition. So that's it from my side. I will be explaining the qubit, the main part, the main crux which I love to explain is which will be explained in the next lecture. Qubit and its velocity representation and the gates, how you manipulate them in the environment and this kind of stuff. So thank you so much from my end. This is the end of lecture number 1.